hit this button over here. Okay, so let's reveal counts. You know what? Let's do for fun. Let's do it with the labels hidden. That's always exciting. Okay, in the first question, big majority on one answer. Very good. So most people are quite confident of the answer to the first one. What about the second one? Again, people are extremely, extremely confident on the second one. Let us see what people said. Let's do it. The label is displayed. In the first one, people said independent. In the second one, so big majority, 61 to 5. In the second one, people said not independent. The correct answer is, of course, independent and independent. Oh my goodness, almost everybody got this one wrong. Everybody said not independent. The correct answer is independent. What is going on here? Let me give you a quick reminder of what independence means. I would say the first one is sort of independent because you sort of think of the red dice and the blue dice as being independent and sort of having nothing to do with each other. The second one, it is true that the answer is independent, but it's not because of that reason. So it's sort of independent for another reason. So the only way to do this type of problem is to know the definition of independence. Independence is a special math word that has a special math definition, and you have to calculate. So let's do the calculation and see how this goes. And indeed, this is a good one. If everybody got it wrong in class, then if we put it on the midterm, then the people who came to class and studied will get it right, and then we'll all be happy, and the people who aren't here will all get it wrong, and we can laugh at them. Okay, let's do it. So the key thing to remember is what is the definition of independence. And last time we did the sort of word definition. So this was the definition of independence. Def apostrophe n is definition. A and B are independent. So the special math word independent that again has nothing to do really with, like, independent in the English language means all sorts of things. In probability class it means exactly one thing. Means the probability of A, probability of A does not change when B happens. And by when B happens, this is the idea of probabilities changing when you observe certain things, like we were talking about last class. The way you'd write this as an equation is the probability of A given B equals the probability of A. So whether or not you observe A, this is given. So the probability of A given B is what is the new probability that A happens now that you have observed B. Just like we saw last class with the cards. If somebody reveals some cards to you, they reveal that B has happened, the probability of A can change. But in this particular situation where they're independent, the probability is equal to what it was before. That's the definition. So if somebody asks you, are two things independent, you really have to calculate both sides of the equation and check, are they equal? I will do a little shortcut. This is the alternative definition, and we just got to do a little bit of algebra here. Alternative way. And the alternative way is to use the formula that the probability of A given B, we derived this last class, is the probability of both A and B happening divided by the probability of B. So this is what we were talking about last class. How do you actually calculate this? How do the probabilities change? And they must change by this formula. The reason why this formula happens is because if B has happened, then any way that A could happen without B happening is impossible. So this was with the intersection. It sort of restricts you to just things where B has happened. And then we had to divide by the probability of B to make sure that the probabilities sum to 1. So that was the formula we derived last time. And if you just plug that in, so you plug that in, plug in. Let me see, can I move this little guy out of the way? Ooh, it can go on the side, okay. If you plug that in, then the formula says the probability of A intersection B divided by the probability of B equals the probability of A, right? So I've replaced the left-hand side up there of A given B with the formula, and now I can rearrange it to get what I call the multiplication rule for independence. Multiplication, the hardest part of probability is spelling. Multiplication rule for independence. Independence. Is that close? Okay, I think that's close enough. Which says A and B are independent, means the probability of A and B is the product of the probabilities. Probability of A times probability of B. And I got this just from the previous one by multiply. So the original definition, I think, is the intuitive one. What does independent mean? It makes sense that it means something doesn't change, something does not depend on something else. And then the multiplication rule is actually very useful. It just has one multiplication. It's a little harder to intuit, but a lot of people sort of think of this as the sort of easiest way to calculate and work with independence. That's the multiplication rule for independence. Any questions or comments about that? Who has seen the multiplication rule for independence before? Okay, some people. So normally this is what people tell you. They just say independence, it just means this. Don't think about it too hard. But in this class, we want you to also know what it means. So it means this, and that turns into this by math. So now let's use the multiplication rule for independence to check and see our two events. So we had A was the event that the sum of the dice is 7. And B is the event that the second dice is exactly 2, I think we said. Okay, and to check independence, we're going to need to calculate 3 things. We're going to need the probability of A, we're going to need the probability of B, and we're going to need the probability of the intersection. The probability of A and B is not so bad. I think it will help. Let me draw a cartoon of the probability space. This is how I would sort of do it. I wouldn't draw every single item. So this is going to be my sample space S, as we've seen before. So it starts with 1, 1, but I'm just sort of going to draw like little dots. 3, 4, 5, 6. So this will be like the first thing will be the first dice is 1, and then the next one will also have 6 dots. And I will just sort of imagine the labels as I need them so to save time drawing. And you could even get away with drawing less than all of them, 1, 2, 3, 4. But I'm going to draw all of them for this class. This is like how I'm thinking about the problem. So I got this probability space. It's got 36 things in it, the 36 pairs. The sum of the dice is exactly 7. This is the kind of thing we did early on the first few days of the class. It's this diagonal over here. So it's the diagonal that has 6 dots. Okay, I guess my diagonal is a little messed up because my picture is a little messed up, but it's like that. So that's the sum of the dice. That's the event A over here. A, I guess I want to draw it with a pen. A, which is the diagonal, and it's got 6 things in it, so the probability of A is 6 out of 36, also known as 1/6. That's the most likely outcome when you roll 2 dice is 7, right? The diagonals can be smaller, but this is the main diagonal that is 6 wide. The second dice is exactly 2. This is also 1/6. The probability of B is going to be 1/6. And actually, I'm going to write the 1/6 as 6 over 36, which is 1/6 as well. And the reason this works is because it is this column. The second dice is exactly 2. So 1, 2, I think it's this row over here. That'll be B. B. Okay. And now the thing is that's exciting is you have to do their intersection, and I can see from the cartoon what their intersection is. It is exactly one thing. So A intersect B, this is both happen. And I can see that this is exactly one outcome. There's only one outcome where this happens. If the second dice is 2 and the sum is 7, then they must have come out 5 and 2. So dice are 5, 2. And that's exactly this thing, A intersection B. Okay. So all of this stuff is sort of review from last week, calculating basic things about dice, just like the homework due this Friday. And you can calculate its probability as 1 out of 36. The probability of A intersect B is 1 out of 36 because there's only one thing, and there's 36 things in total. And now you have these 3 numbers, the probability of A, the probability of B, and the probability of both. And you just calculate, is it true that the probability of both is the product? Does it multiply exactly? And the answer in this case is yes. So notice, let's do this in Poussey. Notice that 1 over 36 equals 1 over 6 times 1 over 6. Therefore, A, B are independent by the multiplication rule. Okay. So we checked it. This was the problem that almost everybody got wrong on mathematize. This one's very tricky. You kind of think of 7 as depending on both dice, right? The sum is 7 in some sense depends on both dice. So if you tell me one of the dice, then maybe the probability has changed. But actually, the sum being exactly 7 is a funny one where there's a 1 in 6 chance of it happening, and there's a 1 in 6 chance of it happening no matter what you roll. So sort of, if you need the sum to be 7 on the first dice roll, what number are you hoping for? Well, you don't care. Whatever it comes up on the first dice roll, the chances will still be 1 out of 6, no matter what. So this is a funny, counterintuitive one. Yeah?
What would be a set of probabilities where really rolling 2 dice like this, where they would be dependent?
Yeah, this is a great question. Let me do a little. Most of the time, like sort of being independent is you should think of as some kind of miracle. So if you just made up something, probably it'll work out to not be independent. Let's do A is the sum of the dice is 3. Is 3, and let's make B equal the first dice, or the first dice is equal to 2. These ones are not independent. Some people say dependent for not independent. In math, you got to be careful with nots. In a class I teach, there's something called a closed set and an open set, and they are not opposites. So you have to say not open and not closed. So I'm going to say not independent, just for greater clarity. And in fact, I think the only number for the sum where it does work is 7. 7 exactly. If it's any other number, they are not independent, and you can just check what the probabilities are. I think this one is 2 out of 36. This one is 1 out of 36. 1 out of 6. 1 out of 6. And A intersection B has probability, I guess it's going to have 1 out of 36 again. And so now when you multiply them, 2 out of 36 times 1 out of 6 is a lot less than 1 out of 36.
Whack. That was
that
me.
That was you? Okay.
That was me.
Great.
I crossed my arms, hit
Yes,
this thing.
this is very good. So,
Mihai, I had a question for you.
yes, please.
The first question, where the sum was 7 and the second die was what was it, a 2?
A 2, yes.
A 2. You went through and proved independence via the multiplication rule.
That's right.
Could you also show us what would happen if I actually worked out the probability of A given B or the probability of B given A by direct inspection?
Yes, this is, well, I think the way you would calculate the probability of A given B, you could either use the formula, which is essentially what we did, or you could look at the picture and sort of intuit it out.
Well,
but
that's what I'm
if you're
looking for.
given B, that means you're somewhere in this row, or in other words, you know the second dice was a 2, and you're asking what was the first dice. And there's only one way for it to happen, which is this 5-2. And then so the chance has to be 1 out of 6 of the conditional probability, because 5 for the first dice is 1 out of the 6 possibilities for the first dice. So if you could work it out like this, or you could work it out and say the conditional probability is 1/6, and it was 1/6 before, and it's sort of 2 different ways, I think, of looking at the same situation.
It's 2 different ways in the sense that the conditional and non-conditional probabilities are exactly the same.
That's right.
And of course, you went with one set of condition, but you could go with the other set of condition and look at.
Yeah. Actually, this is a good point. So if one subtle thing that is sort of coming up in this discussion is the original definition made it look like A and B were playing different roles, right? So the probability of A does not change when B happens, and we have the probability of A given B. But A given B is different than B given A. So it could be that A is sort of independent of B. But if you look at the multiplication definition, now they look symmetric. So A is independent of B is the same thing as B is independent of A, because this multiplication rule shows you that A and B are playing the same role. So if you just unpackage what's going on, they are independent. I think like one way you could do this is you could calculate the conditional probabilities the other way. What is the probability that dice worked out to 2 given that you rolled a 7? It would still be 1 out of 6. Okay. Yeah. All right. Any other questions or comments? Yeah.
For the definition of independence, the probability of A given B is the probability of A.
Yeah.
Does it flip like the probability of B given A
Yeah, so it's one, okay, well, this is a fact that is important to write down. Let's write this fact is so important, we will write it down so there's no ambiguity. Fact, the probability of A given B is not equal to, not the same as the probability of B given A. So A given B and B given A are different numbers. They have totally different interpretations. One is the chance that A happens with some information. One is the chance that B happens with some information. These things are completely different numbers. Do not mix up these numbers. On the other hand, the question you asked is, could you replace in the definition B given A? And the answer is yes, you could, even though they're not the same. And the reason is both of them lead to the same multiplication rule. So the same multiplication rule for A and B with A and B switched is exactly the same. And therefore, if you do the algebra and undo it, you'll get the same definition over here. So the definition works for independence either way, even though the two things are different. Yeah. This fact is related to the so-called Bayes rule. The Bayes rule tells you how different this one is than this one. We'll do that later at some point in the course. Yeah, great question. Any other questions or comments? Okay, I'm going to tell you one more fact, and then Professor Humphrey will take over with probability trees. And this was the multiplication rule for independence, but there's actually a multiplication rule for dependence. So this is the multiplication rule. I'll say for any two events. For any two events. So the multiplication rule for independence only works if the two things are independent, or you can use it to test for independence, right? So in the problem we just did, we calculated these things, and we said, therefore, it's independent. You could use it the other way. Maybe you're given that they're independent in some problem, and you can use this fact. But the multiplication rule for any two events is also very useful in the same kind of vibe. And it says that the probability of A intersection B, it's the probability of A times something, and the something, it's not the probability of B, because that would mean they're independent, but it's the probability of B given A. B given A. And this is always true. I really think of this as if you want A and B to happen, so this is both A and B happen, both A, B happen. How could it be that both A and B happened? Well, first A has to happen. So first A happens. And then once A has happened, what is the chance of B happening? That's exactly what the probability of B given A is. Then given A happened already, B must happen. And the point is, a lot of people miss this conditional thing. If you forget the conditional thing, it does not work unless they're independent. And I will say the proof, what is the proof of this? The proof is rearrange the formula from last class. Rearrange the probability of A given B equals the probability of A and B divided by the probability of B. So if you just rearrange the formula, you get this multiplication rule. And this is, again, this is a really useful enough rule. It has its own sort of name, and it comes up a lot. And in fact, this one is often useful in the way, sometimes you know the conditional probability, something about the problem or something about real life lets you know the conditional probability. A good example is in like medical testing, they'll say, if you have the disease, if A is you having the disease, then our test will test positive 99.9% of the time. So sometimes statements in real life are conditional probability statements, and this rule lets you convert these conditional probabilities into ordinary probabilities. That's the main use of it. And we're going to see this in the so-called probability trees that we're going to do right now in the class. So useful for probability trees and other calculations. I'll say other stuff. Okay. Any questions or comments about any of this before I hand it over? All right. Professor Humphrey, please. And here, we'll leave this one up for a minute. We'll switch to this. Okay, useful ways of attacking probability questions.
Okay, so I think I got that on. I use kind of a combination of slides and writing on paper. I'm a big fan of writing on paper on the dot cam, and I kind of want to get you to writing on your your notebooks or paper. It's just a way of thinking through things. So we're going to do a couple problems today that sound very, very simple, but they will reveal a lot of important connections, almost all attached to what Dr. Nika has been talking about the last couple days. So we're just going to mention useful ways of attacking probability questions and some sort of associated things about these ways. We're going to look at Venn diagrams. I suspect everybody has seen Venn diagrams before. They get taught, if you go in a public school, they're often taught as early as grade 1 or 2. And so we're going to talk about these Venn diagrams, what I call Venn-like diagrams that aren't technically Venn diagrams, but again, they have this visual way of presenting information that is sufficiently close to John Venn's original concept of Venn diagrams. So tree diagrams is going to be what we're going to be attacking here very soon, so-called probability trees. Algebraic notation. So we've been looking at some algebraic notation, and finally we're going to look at some point we're going to look at counting rules. How do we know that there's this many ways of doing something? Arranging different objects, arranging objects where some are of one kind, some are another, that kind of thing. Now, the idea that we've got these useful ways of attacking probability questions, one of the things that is often a question is, how do I know which way to attack the problem? Well, sometimes you're not always sure what way that is the best to attack. Okay, this is part of the idea of problem solving is, okay, you find one line, can we go to another line if that isn't working out? The first two are very useful for thinking out the basics of probability, but then our problems can get very complex on us. Trees can get branching and branching and branching, and the trees get too bushy. But what we try to do is think about how that tree was constructed and then come up with an algebraic way of describing the structure that leads to all that branching. Sometimes with your trees, you don't need to draw all the branches. You just got to figure out the branches that get you to your particular problem. So you are always looking at where are you trying to go? How can I simplify the problem? How can I illustrate the problem? And this idea of being able to simplify the problem into something that you can attack becomes a major kind of theme. So I do post my slides. Today's slides aren't going to get posted right after class because we're not going to deal with very many slides today, but they will go with next class's slides. So, because we're not really saying too much on slides today.
Gary, I think your microphone ran out of batteries.
You think my bat?
Yeah, let's switch.
Yep, it did. It has died.
That's why we have to.
That's why we need to put fresh batteries in each day. Yep, thanks. So we're going to look at what we call two basic ERD questions. And
what an insult to the urn.
What an insult to the urn. Okay, well, we're going to look at these things, and let's just just a second. Actually, no, I'm going to go. Is this one on your computer?
Yeah,
no.
I'll switch this one to your slides.
Let's,
and then we'll leave that one as the document.
Yeah. I want to be on that one for the moment. Okay. So what is an urn? An urn is a bucket. Okay, a bucket, a pail, something like that. Okay. And so, use your artistic abilities to adorn the urn however you wish. Okay. Next point on our basic urn questions is let's Let's attack a couple of these. We're going to attack these with probability trees. Actually, I'm going to switch this one now back to the laptop just so it's on the recording. And here's a key concept that we want to pay attention to is the idea of sampling without replacement versus sampling with replacement. And questions are not always going to explicitly state whether you sample with replacement or without replacement. Sometimes they will, sometimes they won't. And we kind of have to be able to distinguish them. If I pick 3 people to serve on a committee, do I do it with replacement where I could pick the same person multiple times? That would be goofy, right? So that's something that implicitly you should know that that is sampling without replacement. But sometimes it has to be carefully stated. And doesn't matter if sampling is without or with replacement. Well, we will see in many problems it does matter. At a certain point, though, it makes very little difference. What is that point where it makes very little difference whether we sample with or without replacement? And again, this question is just ask yourself as we go through these questions, if the answer above is yes, why? Well, we will see that coming up. So here's our first example. And our urn contains 3 red and 2 white balls. 2 balls are chosen at random without replacement. Now, depending on how you like to draw your urns, I will usually just go 3 red, 2 white. If you are a very fancy person, you might go and go, and then really unnecessary. I think we can just, from that, understand what we're looking at, right? And we're going to select initially 2 balls without replacement, and they're chosen at random. What does it mean to say that they're chosen at random? It simply means that each time we make a selection, each of the balls has an equal probability of being selected, okay? So the idea of random, simple, equal probability of being selected on a simple random sample there. Okay, and so what we want to do is work out these questions. What's the probability both are red, both are white, and there is one of each color? Okay, so I'm going to mention that at this point and just go over to here for a second. Got that. And to set up that we're going to also go to the second problem, which is going to look just like the first problem, except that we're now going to sample with replacement, okay? So we're going to go through, look at sort of how we define things, what we're going to do with the notation on this, and illustrate certain important probability principles with this, with these simple examples here. Okay, so at this point, you know what? I'm going to go back to that one, leave it on that one, and go to the dot camera. And we are abandoning the slides for quite some time now. Okay, so we've got this beautiful urn with our 5 balls in it. So urn example 1. Sample 2 balls without replacement. And I'm not going to write out that they're sampled randomly because we've already written that in the problem, so we're just getting a quick summary here. So let's look at a probability tree now for probably. Not probably, probability tree. Okay, so um, you reach into the urn, just visualize it. This is the thing: is you want to like visualize your experiment, and you're going to reach into that ball, and you're going to grab a ball, and one of two things will happen. Um, you will either get a red ball. Well, actually, I'll put it up here, or you'll get a white ball. Okay, and I'm going to call that. Well, actually, I'm just going to start off by saying first choice. First choice, a white ball, and then don't ignore that one right there. That was just kind of a scribble that doesn't need to be there. What's the probability the first ball chosen was red? 3 out of 5. That should be quick and snappy. 3 out of 5. So there's a 3 out of 5 is the probability that the first ball chosen was red. And what's the probability the second is white? It's, huh?
You said the second is
Oh, it's, the first ball chosen is white. Yeah, first ball chosen is white is 2 out of 5. Okay, so then we go to our second choice, and we visualize what is left in the urn. And again, on our second choice, we can either get a red ball or a white ball if the first ball was red. But what's going to be the probability the second is red if the first one chosen was red? What would you say? 2 out of 4. Okay, so hopefully everybody's just seen that like right away, because you said I removed a ball from the urn, and so I'm only left with 2 red balls and 2 white balls, and so this is going to be 2 out of 4. Now both of the white balls are still left there, but there's only 4 balls left in the urn, so that's a 2 out of 4. But those were the probabilities of getting a red and a white if the if the first ball chosen was red. But what if the first ball chosen was white? Woo. Well, I can still get a red ball on the second choice. But again, now what's the probability of getting a red on the second choice if the first ball was 3 out of 4? Okay, so the idea of doing this tree right now is to make it clear that this is all very intuitive to you, okay? Like, it really kind of makes easy sense as to what is happening here. That's 1 out of 4. Okay, so we've done some pretty good things there. We've got those probabilities. But now what we want to do is we want to attach some notation here. And how should I attach some notation? Well, there's really 2 things that go on here. There's the color that we get on the first choice, and there's the color we get on the second choice. And so we want to define some events in some way. And I'm going to make that first choice. This is going to be event A is, let me just see how I'm going to write this out. Maybe I'll write it down here because I want to do this. I might do something like that. There's kind of like my A and my B. But sometimes I'll do something like that and say, yeah, but is that really what I want? No, I could do that. I could do that. Or I could go something like, or I could do something like this, just to find my events this way, something like Ri is the first ball chosen is red. Now, why am I going to put this subscript R on there? I could have worked with this. These are all, again, multiple ways of defining the problem. And what we do is work with something that we find is easiest for us, but is mathematically correct. So we can't just say, what's the probability a ball is red on any pull, because it was 3/5 on the first pull here, but then it was either 2/4 or 3/4, depending on what happened on the first pull. So I can't just say the probability of a red is 3/5. That doesn't work. But what I could say is that this is the probability. Oops. I could either call that the probability of A, or I could just say that is the probability of a red on the first pull. Oh, a question in the front. Where are we here? Yeah. You can't see it there. Yeah, that's actually a good idea. We'll just keep it on both projectors. Yeah. Yeah, if you have a hard time seeing anything, just let us know, eh? We aren't always certain what you can see, and we want you to be able to see anything. And then sometimes I just get working away on things, and I don't notice that what I'm writing on isn't actually showing up on the screen. So just let us know there. So there was a notation. Now, this one, you see, I could have called this the probability of a white on the first, or I could have simply said, I could have said it's the probability of a white on the first. But in fact, the white on the first is just the complement of the red on the first. So I'm going to put probability of R1 complement there. Because if I didn't get a red on the first, it meant I got a white on the first. Okay, so now we've introduced this complement notation here. And we'll go with the little c in part because Dr. Balka teaches STAT1200 a lot, and he likes the little c. I myself prefer primes, but you're going to see lots of c's when you take STAT1200, so I might as well go with c's. And then sometimes I'll use primes. They're interchangeable. Okay, so then let's go through and then label what are these probabilities here. Okay, so this one is going to be the probability of getting a red on the second, given I got a red on the first. So what we've done is we have applied notation for conditional probabilities. Professor Nika was laying out the notation for conditional probabilities, and just say to yourself, does that make sense? Well, let's go down to this one, because this one's the probability of R2 given R1 complement. Okay, so we have revised the probability of getting a red on the second, given that we have information about what we got on our first pull. Okay, so we've got all that, and we can go through and we can label some more of these things, and you kind of look through this and say to yourself, is Humphrey labeling things right? Pay close attention. I think that looks good. And then this one is the probability of not getting a red on the second, given, oops, you see there's my prime. I like the primes. Given, oops, 1, given I didn't get a red on the first, okay? If you're kind of having a hard time reading some of the stuff I got there, ask your colleague about it. But the other thing is just kind of think it through to yourself. What is the proper notation there? Okay, so what else can we do with this? Well, we can talk then about what we need for solving our problems, which is both are red, both are white. There's one of each color. And what we look at this is we say, well, there's only one way of getting two reds. You've got to follow that branch. There's only one way of getting two whites. You've got to follow this branch. But there's two different ways of getting exactly one of each color. One of each color is you either get a red on the first and a white on the second, or you got a white on the first and a red on the second. Okay? So there's two pathways to getting exactly one of each color. So now let's look at our intersections. Okay. And I will throw in notation here, but again, everything is obtained really just by multiplying along the branches. So our first intersection would be a red on the first and red on the second. That's the probability of two red. I'm going to take the probability of a red on the first times the probability of getting a red on the second, given I got a red on the first.
Hey, why is it okay to multiply the two probabilities like that?
Okay, so what's actually going on there? Well, you just say to yourself, with 60% of the time, 3 out of 5 chances, I got a red on the first. And then I'm going to pick a second ball. And that second ball, half the time I'm going to get a red on that second choice, or half the time I'm going to get a white. And so what I'm doing is taking, 50% of 60%, 50% of 60%, I'm just taking what is the proportion of the first time to get
Yes.
the event of the second.
That was a lovely explanation of the multiplication rule for any two events. Yeah.
Yeah. So we got this, and then so we go like this. We go 3/5 times 2/4, and I'm going to put it on the same line. 6 out of 20, which is 3 out of 10. Okay. We only got a minute. Can I get the rest done in 1 minute? Okay. What I'm going to ask you to do is to just go verify the other intersections. That they are going to come out to 3/10, 3/10, and 1/10, and those intersections are going to add up to 1. So we'll have you verify that. The other thing is we'll be charging into the with replacement case next day. If you want to work ahead, just go through and work out the with replacement probabilities as well.
I'll add, on the very first day of class, I mentioned there's a video where they do the birthday paradox, and it's all about these trees. So if you want to see an animated version of the trees, you can check out that video as well. That's a little refresher. But otherwise, we'll see you guys on Wednesday.